Great. Now I think we're also recording the meeting, and everything is working, hopefully. So what were we talking about? Yeah, I think at least half of you guys already know these fundamental issues, like, what is a bit and how do you store a bit, and, how it is a basis of all information that the computer processes right now. And we're talking about binary computers for now, okay? So we're not talking about systems that have, stochastic states. But you have to bear with the foundational lecture, even though you may know a lot of the stuff, because I believe that there are a number of students in our class who are like total newbies, right? They just heard about computer science, or or they've seen the power of computers. They've seen the power of computers, and they want to know more about it, right? And it's best that we start at the very beginning, so they can actually relate everything to things they know already in their lives. And that's what I'm going to do. And if that is, overkill for you, just feel free to take a break. It's just a Zoom meeting, so you take a break for a half hour and come back. And at some point, if I see the participant list dwindle down to like 3 or 4 people, then I can basically stop and say, okay, well, let's now move on to some of the more serious topics. Okay. All right. So is that good? Everybody okay with that? I'm looking at the chat window now.
That works out.
Excellent. Excellent. Thank you. Great. Okay. So last week we talked about, not last week, last class. It feels like last week, right? Because we've done so much since then. Well, at least me, because I've been reconfiguring everything and stuff. So it feels like that. So last class we talked about how computing really is just processing of information, right? Even if you eventually take the process information and convert that into actionable items and do something, take a drone and deliver a package, all of that, it's all based on actionable information. And also you can think about the physical movements as a processing of the information also, right? So everything is being processed. So how do we get to the place where we are, the first step is basically saying, here is the information I want to process, but in order for this information to be processed, it needs to be stored, right? So last class we were talking about how can I store this information, and one way is, we can use human language like A, B, C, D, E, F, or all the human language letters, the script, but we found, or we eventually converged upon the notion that we don't need 26 letters to store information. Yes, we only need like 2 letters, A and B. All right, A and B, because now I can say that F, F for forest, right? F is A, B, C, D, E, F, right? 6th letter. So I can say that I want to transmit F, or I want to tell F by using 6 of my special symbols. Okay, and use 6 of my special symbols, which are basically 1, 1, 1, and 0, right? Or A and B. Let's just take, instead of A and B, let's say that my A is a vertical line. Okay, lots of people write A in weird ways, right? I write A like this, and someone else might write it, all caps all the time. So let's say there is this little guy kid, okay, who says, no, I want to write my A's because A is the first letter of the alphabet. I'm going to write it with a vertical line. Okay, well, I can't. I don't have any basis for disagreeing with that person. Okay, until they find out that there's more convenient ways of doing this, because this convention and everybody does that in a different way. So that person is going to write all their A's with a single letter, a single line. Okay, and B's, how are they going to write the B's? Well, they could say, I'm not going to write B at all. I'm going to leave a blank space where see, for Daniel says he always uses lowercase, lowercase a, right? So B could be a space. So if I want to write AB, I would just say, vertical line space, vertical line space. Yeah. Okay. So now if I sent you a vertical line space, scribbled on a piece of paper, you would know immediately that it was AB. Yeah. Okay. Now, likewise. But if you think about it, even the letter F, it is coded in as far as the screen is concerned. You're going to look at the computer screen, right? So as far as the screen is concerned, even the letter F, think about a black and white screen, right? Forget about color for now. Is coded in 0 and 1, or on and off, because you can look at everywhere. You can look at every place where you have the F showing. And then if you look at it with a really, really powerful microscope, you can see that they're actually just dots, right? Pixels on your screen, right? You can see that. You take a drop of water and put it on your phone, right? And towards the edge of the drop, where it kind of tapers off, you can get a magnification effect, right? Because the water, clear water, obviously, not dirty water, right? It has a magnifying effect. And then sometimes if you're really lucky with an older phone, right? Not with a retina displays, the older phones, you can actually see the individual pixels on the phone. Or an older computer screen under the water. Right? So this is individual. No, forget about phones. Take an old newspaper, right? Take an old newspaper and use a magnifying lens, right? If you just pull it up like this, you see that the letters that you see are actually just dots, right? And these little dots. So if you go up really close, they don't look like letters. They just look like dots. And you move back up, and you can see the letter, right? So technically, I could in theory, I could encode every single thing I see. It does not have to be a letter. It could be a picture. It could be a picture of my garden or anywhere. And then I could translate that picture into just a series of lines and spaces. Basically forget about lines and spaces, right? We'll call the lines zeros and ones, lines ones, and then the spaces, we'll call them zeros. Yeah, everybody okay with that terminology? Oh yeah, yeah, Daniel. Yeah, it is alpha, but it looks like A. But A derived from alpha, I guess. Okay, so yeah, what was I talking about? Sorry. Yeah, the newspapers and yeah, take any picturesque scene. Okay, and then I have and basically a black and white photo. And if you look at the black and white photo, you just see dots, right? White dot, black dot, white dot, black dot. Now, again, we're talking about a very, very primitive computer in which you don't even have grayscale, okay? It's just black and white. Now, theoretically, it is possible to get arbitrarily clear pictures, black and white pictures, using just black and white, no grayscale. How is that? Right? Because you just need to make these dots really, 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 really tiny, okay? Really tiny, and even though they're just monochromatic, black and white, I can actually make a bigger circle, a bigger disk, pixel, a bigger pixel, right? A bigger pixel, which contains about 50% black and 50% white. Yeah, and then it'll look gray to me, right from a distance. Yes, agree or not? Okay, so we're just reducing everything, factoring all of those things out. You're just looking at the bare bones here, and say that now I can take this entire picture and I can code it up in these rows, right? So my picture has 1,280 rows and maybe 1,280 columns. Oh, 1,280 columns and 1,280 rows. Yeah, like that. Now I'm going to take this picture. Well, actually, let's forget about 8, 12. Let's just 10 by 10. Okay, it's much easier. 10 rows, 10 columns, and 10 rows. Okay, it's a square. That's my picture. Now inside, so I'm going to say the contract between me and you guys is that this picture is going to be transmitted in row major format. Those of you who are doing mathematics and linear algebra and matrices who probably recognize some terminology here, okay? So we have that agreement in place that we're going to do it row major, meaning that I'm going to send you my picture row by row, okay? And you know exactly how big each row is, so that I can send you 100 dots, right, in one line. I send you 100 dots in one line, okay? But you know that every line is only 100 dots, okay? So you take that long 100 line dot line and chop it up into 10 bits and take each bit and put it layer it, not layer it, put them one under the other, and then you get your rectangular or square frame. And if you look in that square frame, you'll actually see the picture that I had encoded for you. Now, this is actually an interesting exercise, and you can play around with it. I think it's called ASCII art. I might be totally mistaken, right? This is like I'm thinking about 20 years ago. 20 years ago when I was learning computer science, I think it was called ASCII art, right? ASCII art, where you create a pretty sophisticated picture. You can go to Google and search for ASCII art, right? Pretty sophisticated picture made up only of ASCII characters. ASCII characters meaning A, B, C, comma, dot, and so on. With that, people were taking advantage of the fact that, a comma has a bit more black ink than a period, right? Or an 8 is darker than, let's say, a 1, okay? And so they were algorithmically calculating from the picture, these little squares, oh, this is like 50% dark, so I need a character that's got 50% black in it, okay, put it there, and so on. And then the whole picture comes alive when you look at it from a distance. So I don't know if you've seen it, but take that to an extreme and say you don't have these individual characters, you only have a dot and a blank, okay, dot and a blank. And you can still do it, right? You can still do it. You just have to go back further so that you don't see the individual dots and the blanks, but you can still get your picture by you assemble your picture. Does that make sense? We need to be on the same page so far before we go on to the next step. Yes or no?
Yes.
Great. Okay.
Yeah.
All right. Thank you. Okay. So that's essentially what we're trying to encode. Now, we know now that it is possible to encode it, right? Because, we figured out a way to encode it by using dots. Now, all we need at this point, at this stage, is the next step of the puzzle, right? How do we encode it? Now, in a way, so obviously I can encode it in many different ways, right? So like my friend and I did back in college, where, light switches, right? This is a really painful thing. The other thing I could do is basically just, assuming that we don't know English or common languages, yeah, I could just, write it out, these ones and zeros on a piece of paper and send it over. It's all, that works, and it's very slow. So what we're looking for is something that is the equivalent of my switching these lights on and off, because that's instantaneous, right? Not instantaneous, it happens at the speed of light, right? But we want that speed of communication. But we also want the ease, right? I don't want to be, every time I don't want to be converting everything into ones and zeros and then go to the wall and switch this on and off. So I say, well, let me try and do this better so that at least I save time. So instead of having one switch, let me have multiple switches. In fact, I have each row in my picture has 10 pixels, right? 10 dots. So I'm going to have a row of 10 dots, 10 switches. 10 switches. So I determined that the first row in my picture has, on, off, on, off, on, or something like that, okay? Then I set all the switches to that position. So I have 10 lights outside my window, right? And they're all blank. I configure the switches first, and then I open the window so that she can see all of the switches, all of the lights, and then I close it again, right? So I've transmitted the first row. Right? And then I do the same thing for the second row. I do this third thing, it's the same thing for the third row. And so I do that for 10 rows. And each time she receives, 10 at a time, right? So she writes it down and then she decodes it. Does that make sense? Yes or no? Well, every time you see me look around, I'm looking at the chat window, right? So you can basically type in there, yes or no, right? And yeah, so as soon as I get about 2 or 3 yeses, I'll proceed. Yeah, great. Okay, thank you so much. All right. Yeah. Okay. Great. Okay. All right. So where were we at? I tend to lose track of it very frequently. Hey, there's, can you guys still hear me? Because there's a train. I hear a train on the tracks.
We still hear you.
You still hear me? Okay, great. Excellent. So, what was I saying? Okay. So I'm transmitting 10 dots at a time. Well, so 10 dots at a time. Now, here's the interesting thing, right? So I don't want to call them dots, right? But these switches, how many possible positions can they have? 2, right? Okay. Now, if they could only have one position, right? They only one position, either be on or off. I can't change it, right? What would be a good name for that switch? It's really not a switch at all, right? If it had only one name, I would call it a unary switch, right? A unary is 1, right? Like the game Uno, right? You play the game Uno. I don't know why it's called Uno. Oh, because there's only one person left in the end, or maybe something like that. Okay, so is that why it's called Uno? But uno is basically one in Italian, or the Latin, Roman, Romanesque languages, I think. Yeah. Okay. So Spanish. There you go. Thank you, Sumi. Okay. So one. So if a switch cannot take more than one state, I'm going to call it a unary switch. Now, believe it or not, the word unary will come back, right? When we start programming, there's something that is unary, and I'll point it out, and you guys can, think about it then. But this switch has two possible positions, right? Two positions. So up and down. And they're both stable. Okay. It's not that one of them is stable and the other one is unstable, right? So if one of them was stable and the other one was unstable, then I would call it monostable. Okay. It's called uno, unary switch, but it's called monostable. Okay. This is mono is one, right? Like Princess Mononoke. Right. So one is monostable, means it's stable in one state, but it's not stable in the other state. So you can basically take it there to the other state, right? Like a pendulum, right? A pendulum has one stable state right here in a gravitational field, right? Which has a single direction, right? So actually, right? So and then I pull it up here. This is another state, but it's not a stable state, right? So if I let go, it's going to return to its stable state, right? So that's a monostable. And if I let it go, and usually what happens is that it doesn't immediately come in and through damping and settle down here. It'll go all the way over there and then go, and eventually it'll settle down, right? So that is a monostable. It's an oscillator, right? So those of you guys who are doing electronics or electrical engineering or electronics engineering, I don't know where they teach these things. But this is called an oscillator, and it's very easy to build, right? You just get components on Amazon for under $5, right? And you can build an oscillator at home, right? And you can tweak the frequencies. And so you can have it swing like this, or you can have it to swing like that, and so on. So that's basically an oscillator. Now, so this switch, which does not oscillate, you can push it to one side and basically sticks. So basically it's a pendulum with one of those geomag balls, and then you have two of those geomag rods on this side, on that side. Okay, so I pull it here and stick it to that, and it's stable. It's stuck there. Right? Likewise, it's stuck there too. Actually, it's not quite true, right? Because there's another stable state in the middle. So it's, trinary, right? But, forget that. But let's assume there's only two stable states. Then I call it a bistable oscillator, right? So it's bistable because it has two states and they're both stable, right? So now I can obviously, and so my switches are basically bistable, right? So my bistable. So, and then if I want to give my switches a name, what kind of switches would they be? Are they unary switches? No, right? So they are binary switches now. This binary is two, bi is two, right? By. So binary switches have two stable states. Now, I don't want to call them binary switches or bitches. I want to shorten it to something that's much smaller. Okay, so I say these are not switches. I'm just calling them items. Right? Items. Now I can shorten it. And say it's a binary item. Okay. So what's a good short form for a binary item? Bit. Thank you. All right. Okay. So I'm going to call it a bit. All right. So any item that can exist in two stable states is a binary item. Okay, and it's a bit. We call it a bit. Okay, so if we had three stable states, we have trinary items, and thankfully we're not there. Okay, so we want to take these binary switches and use them to encode. Now, going back to my hostel analogy, right? So you know that I had 10 of those switches, so I can transmit one row at a time. Now, because of historical reasons, right? Historical reasons and how many switches they can pack and so on and so forth. Intel and AMD and Motorola, all these early hardware manufacturers decided that it's easiest for them, for whatever, I don't know the reasons, you can look it up on Wikipedia, right? It's easiest for them to manufacture these switches eight in packs of 8, right? You go and buy soda, you buy 6 packs or 8 packs or 10 packs, right? So like that, they said, bits are so cheap now, so we're going to sell them at 8 bits a pack, right? And so they said, these are 8-bit packs, and we're going to call them what? Bytes. Okay, thank you. All right. So, and it's kind of cool, right? So a bit, bit is a small, like a, an animal or a pet bit you, right? But a byte is a is a shark. Okay. Just a byte has eight bits in it. So they package these bits in packs of 8. Now, what do these packs actually look like? What do these bit packs actually look like? You can't see these bit packs. By the way, back in the day, or even today, you can build your own byte, and it could be as big a byte as you want. You can look at it, right? You can have, oh, here, I built an entire byte using, a breadboard and transistors and so on and so forth. Okay, so you can actually see the byte. And in fact, you can even put LEDs for each of those switches, so you can visually look at the byte and see what number is being encoded. In fact, if one of you is facile with breadboards or Raspberry Pi and so on, you can feel free to play with it. It'll probably take you an hour or so to put something together. I don't know, you may have to order LEDs from Amazon, right? But you can put it together and you say, hey, look, I've got a byte here and I'm going to try and code the letter A, right? And then the letter A in ASCII, the code for letter A, you can look it up on Wikipedia, right? How they represent A in terms of, on and off. And I believe letter A is ASCII code 65, which you will get to know how to convert these things very soon, right? So 65 would be 0, 1, and then all zeros up to 1 at the end, right? 64 plus 1. So it would be off, on, off, 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 on. Okay, so that's basically your configuration of switches to communicate the letter A. So and that's how I end up storing these things. So, but that switch, that byte is really big, right? So you can store useful information of consequence, right, or significance using big ass bytes. So what you need is a tiny byte, so you can store lots and lots of bytes in a small area. Because unless you can store millions of bytes in a small bag, there's it's very very slim chance. In fact, it's impossible to store anything greater than 1 megabyte. Yes. Okay, 1 megabyte is a million bytes, and even if I take a picture, right? A picture of the outside, a picture on my phone, most phones are now 5 megapixels or 12 megapixels and so on. Yes. And 5 megapixels is that picture is encoded using 5 million bytes, right? Which means that picture, if you break it down and look at it through a super strong microscope, you'll actually see 5 million times 8, that's 40 million dots. Right? So that picture is made of 40 million individual dots. Okay, individual dots. Now, and of course, this pictures are not black and white. So instead of saying that we're just going to use 0 and 1 for black and white, what we'll do is take an entire byte to encode the color. Right? So I could have 256 possible colors, and each byte is 1 dot in a particular color. If it's 0, then it's blank. Yeah. So then I can encode a color picture in 256 colors that is as big as 40 million dots, right? For this 5 megapixels and so on. So far, does this make sense?
Yep. Yeah, I'm fine.
Okay, great. Hey, Daniel actually pointed out something really interesting here, a nibble. Okay, so if a byte is 8 bits, what would I call half a byte, right? So, and it's important to know what a half a byte is, because a half byte is very common. We encounter it very frequently, especially when you go on to CS2B and so on, you're doing bitwise manipulations, right? So a byte is, like that, but half a byte, we're going to call it a nibble, okay? A nibble. But a byte, we didn't spell it with an I, we didn't say B-I-T-E, we spell it B-Y-T-E. So a nibble also will keep the same flavor, okay? Or same mindset, and say, well, a nibble is not going to be N-I-B-B-L-E, it's going to be N-Y-B-B-L-E, okay? It's a sense of humor that we computer scientists have, yes? Okay, so a nibble is just basically half a byte. It's 4 bits. 4 bits is 1 nibble. Okay, so how did we get here? How do dots convert into an image coming out? Okay, Chan, good question. All you need to do is you need to know how many dots per row. Yes, you need to know how many dots per row. So 5-megapixel camera will also have encoded in it's called metadata. Somewhere inside of the file, it'll basically say, well, this picture has, 2,500 rows and 2,500 columns. Yeah. Okay, so then you'll take the bytes, or how many ever bytes you take to encode each dot, and you'll say, I'm going to have 2,500 dots on the first row, right? And then you chop the stream there, okay, and then move it, right? Chop, chop, and then you put all the slices one under the other. Then you get a massive picture. Does that make sense, Chan? Well, I don't know. He's not responding. Okay. Well, does that make sense to everybody else? Oh, I see. Well, you know what? Funny thing is, yeah, it came out here too. All right, but it makes sense, right? The important thing is it has to make sense, okay? Because until it makes sense, the idea does not belong to you. It belongs to me, okay? It's my idea because it is attached to my sense, okay? Not yet attached to your sense, okay? So how do you make all these ideas your ideas, right? Just take them from me, because it's not mine. Well, it's mine, but it's everybody's. But I have 100% right to use it and think about it and enjoy it. So all these ideas, public domains, knowledge is free, right? It's out there, and it's there. It's all attached to my sense, my good sense. Okay, take it, and pin it to your own, uniform. Pin it to your sense. Okay, when it's attached to your sense, it makes your sense. Okay, then it's your. The thing is, when it's your idea, you feel completely comfortable sharing it with others, right? Until such time as it's my idea, many people I find, not mine, until such time as it is someone else's idea, I think many people feel uncomfortable parroting other people's ideas, because, inside your mind, you feel that, it's not really your interest, not your dream that you're communicating. It's really someone else's. Someone told you and you just believed it on face value, and then you're just parroting it to someone else. Right? Maybe you get a temporary high out of it by the other person thinking, oh, that person knows something, right? Or but you don't know. You're just taking something that you heard and you're passing it on, right? So it doesn't give you as much pleasure, right? Even though that other person might have actually understood what the original person was saying, and they said, wow, what a fantastic idea, right? And then you'd say, wow, the person who told me that had a kick out of it, got a kick out of it, and the person who listened to it got a kick out of it, but I communicated the idea and I didn't feel anything, right? So how do you feel it? You feel it because you make it your own. Once you make it your own, when you share it with someone else and they get a kick out of it, you also get a kick out of it. Okay, so that's the way to be, I think. That's my theory, hypothesis anyway. Okay, so if it makes sense, that's perfectly fine, because all that needs to happen right now is for ideas to make sense. It'll be there. If it's stuck to your sense, you can always go back to it and then relate it to other things. This is like a jigsaw puzzle, right? You have lots of puzzles pieces out there, right? And people are handing out these pieces for you to complete the big picture. And then you take a piece, and then if you give it off to, if you give it to someone before, you don't take it, you don't have it, but you don't know where it goes yet, but still you take it and stick it to yourself, so that later on, when you find that, oh, I need a piece there and it's missing, but you still have it because there's something that made sense, you didn't throw away, you have it in your garage, your attic, then you go and pull it up and put it there, that completes the picture. Does that make sense? That's how most of learning happens, I think, at least for me anyway, right? So if there's something that's interesting but not immediately useful, what I do is I don't forget it. I just tuck it away in the back of my head. Okay, I just tuck it away. Later on, when I need something, then I would go to look at all the interesting things that I have that fit in that area. Okay, and then I find something and I put it there, and so that's I found a lot of things work out like that for me. Okay, maybe for you too. So which would be really cool. Okay, so no, I meant for RGB values, not the color itself. Okay, all right, cool. Great. We'll talk about RGB values in later. Someone had a question, right? So we'll talk about all that later. Augie. Okay. So where are we going with that? Okay. So now we have this whole idea of being able to communicate these, ons and offs, ones and zeros to the other side. The challenge now is being able to shrink our switches down. We need to do two things, okay? We need to shrink our switches down so that we can pack a lot more of these switches in a small area, So that's essential, right? So that's essential, because until we can do that, a computer is still possible. You know, I can build a computer, an entire computer on a piece of paper. Well, assuming the piece of paper was long enough, because as we just saw, well, I just need to keep on writing ones and zeros. Maybe I'll use up a 15 million page notebook writing that, but it's possible, right? And maybe I'll take 5,000 years to do it, right? Assuming I was uh, uh, immortal or something like that, right? So I can do it, but it's just tedious and long, and probably I'll give up, because I'm a human, give up and so on. But the important thing to keep in mind is that it is possible. It is possible to store arbitrary amounts of information on media. It's an arbitrary finite amounts of information on finite media, right? It may be longer and bigger and cumbersome and tedious, but it's possible. Now, that is the biggest step, believe it or not, right? So that is the biggest step ever in computer science, right? Because, everything else is, you need to cross that first step. After that step, you have a lot of different options, and, you can go this. That step needs to be mastered. That needs to be crossed. Okay, so we've gotten to the other side. Now we know it is possible. Right? And all of science too. First, it needs to be conceivable. You have an idea. The first thing to do is it needs to be conceivable, meaning that it's not logically inconsistent. It doesn't have any contradictions. It is actually useful, and it's something that you need to do, and it's possible to do it. You can envision it, right? If it's not even envisionable, right? If it's not, it's inconceivable, and you don't have any idea what you're building, obviously you're not going to build it. Yes. So the first thing to do is establish the fact that it is actually possible, right? Maybe not by us, maybe, right? Keep this in mind. Maybe we've established that the computer is such a device as possible, but maybe we won't be able to build it for the next, I don't know, at the current rate at which science and technology is evolving. Maybe we've established that, it's possible to build a computer, but we cannot build it until, the year, at the current rate, for the next 3,024 years or something like that. Okay, maybe if we had such an accurate model of human progress, maybe we'd be able to see that. But believe it or not, that actually happened, right? Because we know, we go to these ancient civilizations, Egypt and India and China. We see a lot of work that has happened that is actually algorithmic. They are creating something or calculating something at the abacus. The abacus is basically an algorithm, right? So you can perform complex numerical calculations on an abacus. Now, who knows how old an abacus is, or many thousands of years, I guess, right? So and you can calculate the square root of 47 or something like that on an abacus. I hope I'm right. I don't know, but I'm pretty sure you should be able to do that, right? Someone who knows how to use an abacus can chime in. But is it possible to? Right, but if you try and ask someone, can you what's actually happening? How do you get the square root of 47? You're just moving some beads along and you get 47 square root. How does it happen? So you don't know how it happens, but if you follow this dance, this choreographed dance, yes, this is multiple dances, right? It's a square root of 2. There's not just one way of doing it, because the abacus is thousands of years old. One school of thought might have said, use this way to get the square root. Another school of thought might have said, use this way. So all of these dances eventually lead to the same number, the square root of 2. Right, 1.414. But they're all very strictly choreographed dances. You got to follow the steps one after another, because if you don't follow the steps, you're not going to end up there, right? You may fall off the stage or something like that. So that is a pure algorithm. Someone has a question. How do you find the dances in the first place? Thank you, Augie. Okay, so these dances are basically created by the inventors. So how do you create a new dance? As you go to a show in San Francisco, or you watch a dance on Facebook, right? You see exquisitely performed dances, beautiful dances. Have has story and emotion and everything built in, and there's usually the expressions. But who designed these dances? Who? So someone had the foresight to think about it and come up with a way to design these dances. I said, wow, this is useful and beautiful at the same time. I'm going to publish it. right? And once it's published, other people will also start using the dance. So in the same way, some ingenious person in ancient China or someone, they came up with a way of saying, oh, well, you know what, we have to make these triangular structures, 45 degrees, right angle, but in order to calculate how many bricks I need, or how many, so I need to calculate the square root of 2, and how do I do that? And maybe some ingenious guy came up with a way to say, well, here's a way you can calculate the square root of 2. Likewise, here's a way you can calculate pi, things like that. All of these things have happened in the ancient world, right? Why is it? Why do I call it computational? Right? It's inside the beginning of computation, not just with Ada Lovelace or Charles Babbage or things like that. You go back all the way to Panini in ancient India, or China or Egypt. So you find these incredible feats of intellectual accomplishment that use algorithmic knowledge. An algorithm is just like calculus, right? So what is calculus? People, how many of you are doing calculus in math? A lot of you, right? Or you've heard of calculus, right? You've heard of calculus. And most people, when they talk about calculus and think about calculus, they're thinking, oh, calculus means differentials and derivatives and integrals, right? dy by dx and all these symbols, and immediately they say, I'm going to shut the door and get the hell out of here, right? But no, calculus, the word calculus, what does the word calculus mean, right? Someone said, Latin or Spanish before, right? What does the word calculus mean? Don't look it up, okay? Just take a guess. No, calculus does not mean change. Calculus does not mean change. No, calculus does not mean computation, right?
Calculating?
No, calculating actually comes from the word calculus, okay? So it's interesting, isn't it? You learn all these interesting historical things in my classes. I don't know if you want it or not. If you don't want it, just have to send me a note and I'll, but the word calculus comes from the word, Latin word. I believe it's Latin, right? Calculi. Calculi, or I don't know how they pronounce it in ancient Latin, right? It's called calculi, right? Calculi does not stand for counting. No, thank you, Flavio. Calculi stands for pebbles. Yeah. So now you can Google, define calculi. They're pebbles, right? And what's the relation between pebbles and calculus, derivatives? Because in the ancient days, calculation was actually driven by something like an abacus. They used little pebbles, right? Moving pebbles around, and that's how you calculate things, by moving pebbles around. And you say, hey, I got 15 sheep at the market today, right? And then, you don't say 15, but you would say, calculate these things. You show them a bunch of pebbles. Okay, so calculus is basically just shuffling pebbles around. Now, when you're shuffling pebbles around, just like the abacus, right, you don't know how you get the answer, pretty much like deep nets, right? You don't know how to get the answer, but not you, but the person who invented it knew. Right? The person who invented the procedure knew, well, by doing this, you actually get the answer, and that's why you get the answer. But the magic, the beauty of this whole thing is that users don't need to know. They just need to know how to use it, but they don't need to know why, right? So you know how, but not why, and that's calculus. Okay, so that, for me anyway, calculus means a procedure or a formula to do something, to get a result, and it works predictably, but you don't know, or you don't need to know, right? Let's say you don't, I don't want to say you don't know, because eventually you'll know, but you don't need to know. You don't need to know how it works, but it'll work. Okay, that is calculus. Now, usually I discourage, right? People from, don't use things that you don't know how to use, right? But, calculus is exactly that, because, you take you have a parabola, right? You have a parabola, or any curve, and you want to calculate the slope of the curve, the slope of the curve. Slope is, what's a gradient? When you're driving a car, you want to go up the slope, high slope, meaning you got to, you waste a lot of energy, not, use a lot of energy, right? So, but a curve is not straight. It's, it's changing, and the slope of a curve changes all the time. So, but if it's a random curve, it's really hard, right? So you find the slope. But if it's a regular curve, the curve, right? Maybe it's a parabola, right? Parabola is like that, like that. So if it's a known curve, then if someone asks you what is the slope of that curve at this place, right? If it's a random curve, you can't tell. But if it's a known curve, and you say, oh, well, if the curve itself is at these locations, then I can mathematically calculate what the slope is at that point? What is the slope of a curve at that point, right? You can't, because the curve is, it's turning all the time. You can't tell. So in order to find the slope of a curve at a particular point, you need like a super duper powerful microscope, an electron microscope, an infinite microscope, right? You go all the way to the little dot, right? That is at the place where you want to measure the slope. And then you want to see, well, it's not even dot, right? So you want to see what the angle of the dot and its immediate neighbors are, right? So you want to see that angle. How do you calculate that? Now you can, from first principles, you can think this through and you can come to the answer. But you can actually apply also, the derivative formula. If it's a polynomial, you can just say n times x to the n minus 1, right? I think that's right. Just for no other terms, just x to the n. So you can calculate the slope using that derivative formula. But you didn't know how you got it, but that is the slope, right? The slope of the parabola x squared at any time is 2x, right? The slope of e to the x at any point is e to the x. This is incredible, isn't it? E to the x is the magic function, right? The slope of the function at any point is equal to the value of the function itself, right? That's not the case for anything else in the world, right? So even take a straight line. The slope does not have to be equal to the value of the function, right? At every time, every place. Not, obviously at one point it's got to be the same, right? But it's not the same at every place. But for e to the x it is, right? Parabola y equals x squared, the slope is 2x at that point. And so, but you don't know how to get it. So that's why it's called calculus. So when you develop a whole field of mathematics, saying here are a bunch of formulas that are internally consistent, right? So you can use them and you can use them in combination. You can put things together. I can't tell you how to make a single one. You can find out for yourself. You can go to the first principles, and find out for yourself. But using these, you can build more complex structures, right? Just like Lego pieces, build these individual Lego pieces and you give them to people. So these are the individual pieces. You can build a gorilla or the Eiffel Tower or the Empire State Building or the Taj Mahal. You build these with individual Lego pieces, but I'm not going to tell you. Yeah. And that's really a calculus because you don't know how to get the pieces, but you can use them together. So likewise in calculus, you can use all these pieces, all the individual rules of calculus and build even bigger things using that. Now, how did we get talking about calculus here? Sorry, I totally forgot. Okay. So the switches, they come in 8 packs and they're bytes. Now, with the advent of transistors, right, that could previously, the very first switches, the ones that you're going to put together, I suppose, in using breadboards, they'll be bulky, right? You can see these switches, like I said before. But when we found that we don't have to have these individual bulky big-ass transistors, I can actually take a plate of conductive or semiconductive material, and I could use a pin or something to scrape a little bit off here and here and here, and then a small area on that sheet of conductive material, I actually turned into a switch because I scraped off the conductive material here and here, so I got a little switch right on that board. Right? It's possible. Right? This is painful. It's a painful process, but technically it's possible. Like silicon, right? Someone said silicon. Yeah, Giorgio. Right? So it's a semiconductor material. So now I've managed to shrink the switch down a little bit. Now it is possible to now not use a pin to scrape off. You can use laser and other advanced techniques to scrape off microscopic amounts of this material. So you can shrink the switches down even more. Right? So likewise, so we developed the technology to make the switches smaller and smaller, so nanoscale, right? So on one sheet of silicon, you can scrape off these tiny, using lasers and scrape off, and then you can start fitting more and more switches on a single plate. Now to the point where you can get an iPhone, right? So my iPhone, where's my iPhone? Yeah, okay, it's over there. Well, I'll get it next time. Okay, so it's about this size, right? So you can see it's about half the size, half the size, yeah, like that. Okay, so in that okay, right. So well, actually, it's not even. So the switches are not even that size, right? The switches are the switches inside my iPhone are inside of a chip, and the chip itself is about the size of a single key on your keyboard, right? That little square, okay? So chips. So those chips, they contain billions of transistors, billions of switches now. Those chips contain billions of switches. So can you imagine, right? Right? So on my phone, which is a 64 gigabit, 64 gigabytes, right? My phone has 64 gigabytes of memory. Like, most people have iPads that have 256 gigabytes of RAM and all, right? Not RAM, memory. 64 gigabits, a gig is 1 billion, okay? Yeah, 512, there you go, right? A gig is 1 billion, okay? And I have 64 billion, and they're not even bits, they're bytes, and it's a 64 billion eight packs. I have, so 64 times 8, that's 480, it's about half a trillion, right? So I have a half a trillion. Inside of my phone, there are these, memory chips, and inside each of these memory chips, I have, not each of them, right? Inside my phone, there's 3 or 4, maybe I think I have 4 chips. I haven't opened my phone, right? In those 4 chips, I have half a trillion switches. I got to give you a couple of seconds to just get over that, right? So I have a trillion switches inside my phone. And here's an even more incredible, mind-blowing fact, okay? So these switches are inside of, who's this, Sandeep? How do you want to be called? You have an alias, Mrs. Richmond or Sandeep? Well, my chat screen went away here. What happened to my chat screen?
Sandeep.
Sandeep, okay. Why did it say, so why do you say, all right, so here you go. I thought I found it. Do you have an alias thing here? Okay, anyway, all right. How come it's showing up on this screen and not on the other screen? How come there's a lag between the 2 chat windows and they're both on the same network? Let me see, hang on. Give me 1 sec, okay? How come the last message I have on this screen is from Augie, and from here, oh, okay, all right, yeah. They're in sync, but it's one of them came through privately. Okay, all right. What was I saying? Yeah. So, where I said you take that panel of silicon or some material and etch these little switches by scraping away microscopically with laser, right? You're just designing these switches on your silicon wafer. It's a wafer, right? It's a thin wafer. You're designing these switches, and that's how you do it. So you use your laser and a plan, and you print from your computer. The laser is driven, and it'll cut out these switches. And you have half a trillion switches in something that only occupies that much space. Okay, that much space, half a trillion. So the more mind-blowing fact here is that not only do you have a half a trillion switches in this area, you can control specific switches in that bank of a half a trillion switches. Suppose you said, well, you've given me a half a trillion switches. I want to turn on the switch which is in position 1,473,000,000. Okay, so you can't even see the switch, right? So this is a tiny switch, and it's surrounded by almost half a trillion switches, and you want to turn on the 1,473,000,000 switch. Okay, so imagine that's your challenge. Now you got to figure it out. Not only have you got to figure out a way in which you can turn that switch on and off, but you also have to figure out how to do it really quickly, because once you figure it out, I'm going to ask you to keep turning on and off these switches. I'm going to ask you to perform a choreographed dance where you go on, off, on, off, on, off, off. So you got to do that. You got to do it really, really fast. So something like you got to turn on maybe a couple of quadrillion switches. Now you're not even talking about, because you got a half trillion switches, and you got to turn on and off, on and off, on and off. Right? You got to do this so many times in 1 second, right? So in a millisecond. So in a millisecond, I'd like 97,000 trillion switches to be changed, right? Same switch more than once, maybe, obviously, same more than one, right? But in a millisecond, I want that many switches to change their configurations, change the positions, go from on to off, and then on again, and so on. So this is a mini dance. I want to choreograph that, and it is possible to choreograph that to that level of detail to happen on any device, on my phone. Every time you look at your message, right? Someone sent you a message and you get that bip, that sound in your ear. That's a delicate dance. performed by, a half trillion or so many switches on your little phone. They're all saying, oh, something just came in from, Janice to Robert, okay? And let me do this little dance to alert Robert that there is a message that, she just sent, right? As you hear that ting, but that is basically because the message came in, the wireless signal, triggered a switch, and that switch triggered neighboring switches in a particular way, right? And those neighboring switches then started performing this dance, and then the dance eventually started propagating to the speaker on your phone, and the speaker emits a beep, right? And all of that happens in a couple of milliseconds. And then you hear it. So, how crazy is that? Right? It's incredible, isn't it? So that is the kind of power. It's a kind of power you get. And obviously, with great power comes great responsibility, right? Because, when you have that kind of power, especially with C++, in C++, you can do that. You can do these kinds of micro dances, right? You can do these dances in C++ you can't do in many other languages, right? Higher level languages. You get that power, but because you get that power, you also get the ability to do wrong things, right? So you can basically dance off the end of the stage and fall into an abyss, right? Or you could do something really horrible and screw up your screen permanently, right? Increase the energy rate. I don't know if the current is controlled electronically, but maybe you can, burn up your monitor or your display screen, you screw up your keyboard. All of that is possible to do using the software now. You don't have to go and hit it with a hammer, okay? Once upon a time, someone used to say, what's the difference between software and hardware, okay? And I think someone else in the forum maybe responded saying that, the bits of your computer that you can hit with a hammer, that's hardware. But the bits of the computer you can only swear at, okay? That's software, okay? Because, eventually you're going to get to that place where, your program just doesn't work and you want to take your whole computer and toss it out the window. No, don't do that. Don't do that, okay? Just swear at it because, your computer is cool. It knows you're not swearing at it. You're just swearing at yourself, really. You're in a room and you're swearing like hell and nobody else is there. Who are you swearing at, right? The computer doesn't care. Okay, it's like the Buddha said, right? So someone said to the Buddha, "Well, all these people are, are insulting you and saying bad things about you. What do you do?" He said, "Yeah, I just don't accept it, right? I don't listen to it. Okay, so if someone gives you something, you don't take it. They're stuck with it. They have to have it, right? So I don't want it, man. Keep it. Okay, so like that." The computer doesn't care, so you can swear at it, but it's okay, swear at it. Eventually, you'll cool down. You'll cool down, and then you'll see, that. In fact, when you're in a swearing mode, you will not be able to debug your code. how crazy is that? Okay, so a bug will make you frustrated. But when you're frustrated, you can't solve the bug. That's the irony of life. So even life, right? When you have a really, really tough time, you're really down in the dumps, you can't see a solution, right, to your life problems because everywhere around you, you just see walls. You're in a hole everywhere around you. So nobody's helping you, right? So, but in order to solve your problem, let it lie, right? Don't give up hope. And then, when you rise up, you can see all around you, then you can solve your problem. So when you're deep in the dumps in a bug, you can't fix it. So I think DDA, one of my 2A students who went on to do 2B and 2C, right? So he made this observation when he was fighting with a very, very difficult 2B quest, okay? So apparently he was banging his head on a brick wall for a long time. And then he said, fuck it, I'm just gonna go and take a walk, okay? And then when he was walking, he found the solution. And then, when you walk, you forget about it. Forget about it and you cool down a bit. When you cool down, you're not frustrated. Right? When you're not frustrated, then you say, okay, well, you know what? I don't really care if I'm going to solve that quest or not. I don't care if I pass 2A or 2B or 2C. I don't care really because life has opportunities. If not this opportunity, some other opportunity. I'll do that. I'll do this. When you get to that place, then you're able to solve the old problem too. Right? So you can start thinking, well, now that I don't have to solve the problem, let me see, can I solve the problem at all? Because, it doesn't matter if I don't solve it, but if I solve it, that'd be really cool and interesting, right? Then when you think about the problem with that mindset, you can find the solution, right? But if you think about the problem with the mindset saying, well, this problem, I'm like this, super duper coding cat, right? I know everything. I can't be defeated by any bug, right? If there's a bug in my code, I'm just gonna go on top of it and squash it, right? I'm gonna defeat every single bug I find, okay? That is never a good strategy, right? Because as I think I made this point in CS2C, he who rides out to defeat has only defeat left to meet, right? Because, don't try to defeat anything, just try to find things out so you can enjoy it better. Then you have a much better chance of finding the thing. So don't try to squash the bug, to kill it, but just try to understand it. Just try to understand it and say, well, if the bug was gone, maybe I would have enjoyed it, but too bad the bug is there. And then you'll find a solution, right? You can also ask in the forums, but oftentimes I find people asking, they run into a bug and they'll immediately post in the forums their code, saying, well, I have this behavior from the questing side, or some program, some product I'm building, I have this behavior, but that's not the behavior I want. But what do I do? How can I help you? I don't know what you're doing, right? So you just say, this is what I need to happen. How do I do it, right? And then say, this is what I need to happen. This is what is happening, and how do I fix it? Even then, nobody can help you, right? You need to know. You got to say, this is what I need to happen. This is what is happening. This is what I'm trying to do to make it happen. That, now we're talking, right? We're getting somewhere. Now, when your friends, your classmates, your tutors see what you're doing to try to get what you're after, then they can say, okay, that's not the way to do it. You can do it this way. Yes, does that make sense? That is the right way to ask questions, right? Never ask a question in the forums. I'm not talking about Reddit, okay? So pretty soon you're going to be on, Stack Overflow, or all these other professional circles, and you're going to be asking questions there. And the best way to ask a question with a high likelihood of getting an answer. So that's what I mean, right? So in my teaching style, here's how you should approach it. Now, when you're done with computer science, well, not done with it, you never get done with computer science. When you're done with CS2C, right? It's not, I wouldn't say 2B even, right? You're done with 2C, you're going to find yourself increasingly on these professional forums. Now let's take Stack Overflow as an example, right? Stack Exchange, Stack Overflow, right? So on Stack Overflow, and you're going to be asking questions, and you're going to be answering other people's questions. Now, it's an open forum. All these forums are open, right? Reddit, Quora, Stack Overflow, all these people have done these incredible things and made them free for everybody, right? Because it doesn't cost a lot to run these things, right? My questing site, it probably costs about, 30, 40 bucks a month. So it's basically free. But free, the freeness comes at a small cost, right? It's not even a cost. It basically comes with an understanding. Like when Google, created Google and they released it, and they had a grand ideal in their mind, do no evil, right? And they said, all you need to do to be able to use our services is just be good, right? Don't use it for malicious purposes. Don't use it to insult other people and so on and so forth. Then you continue to use it free, right? So, and that's how many of these services start. And so in Stack Overflow, you can go contribute, but you need to have practice, right? So it's not enough to just be told. It's not enough to go to the rules page of Stack Overflow and say, all right, these are the rules I need to follow. And then every time you make a post, you need to check the rules. No, it doesn't work like that, okay? So you need some practice and a playground where you can run around just like you would be running around in professional circles, but it's not public yet, in the sense that people are not looking there. Or even if they're looking there, they know that you're practicing. It's a trial run for you, right? So they're looking at it in a very with a very sympathetic lens, right? So this is a learner, and look how fast they're learning, right? And so on and so forth. So where was I going? So yeah, so treat the forums, Reddit forums, as basically just practice, and that's my intent in providing this forum. This is setting this whole thing up for you in a public place, is because previously in Canvas, people would only kind of talk in Canvas, and people have this reassurance in Canvas that it's all private, nobody can see it, I can say what I want, I can private message the instructor and tutors, I can and then it's not real practice for being real software engineers, right? If you want to be a real software engineer, it's not enough to just code, because with just coding experience, even you can know C++, to the bottom, from the bottom to the top, you know everything. But you won't be able to do great things in C++ until such time as you start collaborating or using other people's technology, right? Because you to look at any great thing, it's not built by one person, it's built by many people, right? And they all need to know how to interoperate, work with each other. So and where does this happen? It happens in a collaborative forum like Slack inside of a company maybe, or on forums like Stack Exchange, Stack Overflow. You need to know how to interact and treat Reddit as a playground or practice training ground for that, where you have someone like me and some of your more experienced classmates, right? So who are on it, right? I even have people that did my 2A and 2B and gone on to 2C who are coming back to help you guys in 2A and 2B, although they don't have to, right? And all of us are keeping an eye on the forums, not from the perspective of policing it, right? And kicking people out and telling you off. No, it's because we want to train you to eventually become awesome participants in the real public forums out there, right? So people would say, hey, look at Sandeep's answer to this question, link to it, you get like 5,000 votes or something like that. And so that to get there, go here and here we'll be watching. And as much as possible, I can't keep an eye on every single post you do. And likewise for your classmates also, right? They can't be looking at everything you do. But when we see something that looks like it's not the right thing to say, if it was Stack Overflow, I would point it out, right? Or your friends would point it out. And you have the option to delete it immediately, right? Or adjust it or edit it or things like that. So that's how I treat it. So how did we start talking about forums and discussion, what we were talking about before? I forgot. Yeah, we were talking about information, representation. Someone help me out, okay? So someone help me out. What is the, talking about bits and bytes. All right, packed. Yeah. Okay, so we packed all they come in these bytes, and there's so many transistors, and then this choreographed dances inside of your phone. All of that happening to deliver the experience. Lots of calculations. Yeah. Okay, so lots of calculations happening on your that you don't even see. Anyway, let's leave that alone. We'll come back to it if I remember. But essentially, that's what we're after. We now know how to store the information. Right? We don't know yet how to store all the information. That's what we're going to get to after this. Okay, we know how to store the information, and we know how to process the information. Now, the way you store the information again is again very simple. As those of you who have done electronics or learned about electronics find it simple. But for those of you who haven't, if you can envision it like this. I think you can. I'll use an analogy. I hope you've seen irrigation systems in your garden. Okay, irrigation systems where you have a sprinkler. Okay, a sprinkler sprinkles this way first and then that way next. Okay, it keeps doing that. Okay, well, not in between. Okay, here and there. Okay, only two states. How does it do it? So it does it because, do you know how it does it? Have you taken apart one of those valves to see how it does it? Has anybody taken apart the valve? Okay, the water flowing through. It's ingenious, isn't it? Okay, the water current blasting through the pipe is hitting a vein. Okay, it's hitting a vein. It hits the vein as it's coming through, and the pressure of the water pushes the vein to the other side. Okay, and the water goes through. Right now, it's engineered in such a way that when the water goes to the other side, it's going to start pushing the other side of the vein, so it comes back to the side. So the current is responsible for making the switch go that way or that way. Does that make sense? Can you picture that in your head? Yes or no?
Yes.
Okay, that's exactly what happens in an electrical switch, right? Well, not an electrical physical switch that you have to move and no, I'm talking about a transistor, an electronic switch. Okay, in an electronic switch, the current, there's almost a one-to-one analog between water currents and electricity, right? So you think about it. Water current the current flowing through a tube or a pipe. That's the current. Let's see, electrical current, right? Amps. And what is the water current is made of water molecules. Electrical current is made up of electrons. Well, actually, strictly speaking, I think it's not electrons, it's holes, right? It's because electrons just jump one place. I don't know, right? So that's the electrical current. But the water won't flow until someone is pushing the pressure, applying pressure on one side. The water doesn't flow through the tube. What is the equivalent of the pressure in electricity? What's the equivalent of the pressure? Volts, thank you, Augie. All right, volts. Voltage is the pressure. Because high pressure is high voltage. It's 220, 110 volts on the wall, right? So if you touch it, it's high pressure. It's not so high that it will kill you, but you can go to a water. Actually, yes, I don't know if it's true or not, but apparently, and someone who's in the Navy, I don't know if anybody's been in the Navy and if you have any vets from the Navy, but apparently this is true, right? If you're in a submarine, right? If you're in a Navy sub, that's very, very deep, thousands of feet deep in the ocean, right? And the wall of the submarine has a crack, a hairline crack. You're not talking about a big crack, a hairline crack. The water, apparently, maybe it's possible to calculate that using physics. I don't know. Ooh, think about it, right? So the water at that depth is going to come, spraying out, not spraying out, it's coming out through that crack, that thin sliver of a crack, with that much pressure and velocity. It's like a sheet of glass that if you were to stand there, it'll just cut you in half. Right? That is, and I think I'm likely to believe that, because if you just take a paper disc, right? If you take a paper just made of ordinary paper, right? Paper disc, and you stick it in the middle of your very high-speed drill or high-speed rotary machine, right? It's just paper, flexible paper, and spinning fast, right? The edge is now sharp enough to cut another piece of paper. You can basically just cut a paper using paper because the other one is spinning so fast. So, and it's spinning so fast because, by spinning, you're basically making use of inertia or, centrifugal. There's no real thing called centrifugal force, right? But let's just say centrifugal. You're using that force to stiffen the paper and make it cut. It's the same way that you have high pressure water coming through. Water is coming through so fast that it is so strong to cut through anything. So that's the pressure of water pressure. Likewise, high tension lines have a lot of pressure, so they can force a lot of current, a lot of electrical current through even small pipes. Small pipes have high resistance, right? So small pieces of wire have high resistance. How do you make low resistance wires? Make them of better conductive material like silver, which is expensive, or you can make the pipes bigger. So I don't know if you've ever gone to visited. What is this? Reddit, Lake, no, not Reddit, Redding, Lake Redding. What's the name of the lake in Redding? No, what's the name of that mountain or hill or that place we go to? Lake Redding starts with a T, I think, not Tahoe. Anyway, so they have they have a hydroelectric station, right? Have a hydroelectric station where they generate electricity from turbines that are spinning because of water rushing down to one side. As the turbine spins, right, and generates electricity. But if you look at the wires, the copper wires they use to make the turbines, the coils, you'll be surprised, right? Each one of those copper wires, if you cut it, the cross section, the width of those copper wires is that much. Right? So, even if I had a 1-inch thick slice of that copper wire, I can carry it. It's going to be so heavy, right? So the copper wire is so thick because that has to carry the current that will eventually feed, half of Tahoe City, not Tahoe, whatever that place is, Redding, okay? So all the households in that city using electricity coming out through our walls, okay? And through our walls, we only have these tiny wires, right? So to our plug points, to our power sockets. But each of those wires carries a little bit of current. But outside of my home, all of these wires need to join, just like, tributaries in a river, right? They join, and the tributary, when they join, can't be thin again. Yeah, it has to be widened, right? So if you look at the wire that goes from from your street to the transformers or the power station, they're thicker, right? They're thicker because it needs to carry the current required for the entire street or something like that. So now you can imagine how thick the wires must be to carry the current through an entire city, right? So it's got to be big ass copper tubes, not tubes, and copper bars. So the voltage is the equivalent of pressure, and electrical current, water current. So anytime you're confused about how electricity works, think back to how you would do it in a physical system, right? Of a physical, that's physical too, but physical system that you can actually see and relate to. Yeah, and I say this because when it comes to binary, many people will, when they struggle with making binary calculations, exactly the same thing applies. I say, if you're ever stuck with binary arithmetic, just think back to what you would do in decimal, in base 10, right? And it's exactly the same. So never panic when you're working with binary. Just think back to base 10. What would you do in base 10? You do the same thing, except you don't have 10 letters. You only have 2 numbers, right? 0 and 1. And exactly the same techniques would work out. And if you're interested, we can work through a couple of binary problems later today, all right? Converting and adding and so on and so forth. What time is it now, by the way? Oh, it's 9:25. Yeah, we got more than an hour. It's fantastic. We got a lot of time. Okay. So we'll do those things, and then I'll point out again. So you're saying that you can think back to decimal, and this is how you do it in decimal, and you can do the same thing in binary, and you'll find it works just perfectly. Okay. So, all right. So now we have the ability to not only store these big banks. Well, class ends at 10 o'clock, I think, and 9:50, is it? Okay. Now, yeah. Obviously, it's 9:50, even though it's all online. It's 9:50, so we still have more than an hour. And by the way, okay, so even though we only have an hour, more than an hour, that much time left for this class, I am.
That's 30 minutes.
How many?
30 minutes left.
30.
Oh my gosh! Yeah, it's 9:50. Damn, I was thinking it was 8:50. Okay, all right. Well, let's try and get through the material that we need to. But what's left over, I'm happy to talk about during the first part of Tuesday's class, or even better, if enough of you want to carry on, I got some time later today because we had a curriculum committee meeting at 3 p.m. No, 1:30 that got canceled. Okay, so I got time. It doesn't have to be at 1:30 because something else I need to do later, I could do at that time. So I actually have about 2 hours, more than 2 hours really, of free time. So pick a time that you guys want. I'm happy to talk today, tomorrow, over the weekend too, right? Well, now it's so easy to have a class. I don't have to drive all the way to Foothill, right? Just need to make sure to be home that time. Then I just need to come back here and sit down and we have a class. We have a class anytime. You have infinite lecture, okay? This is in 2 ways. You can have infinite synchronous lectures. How about that? Okay. Yeah, office hours. We do have office hours, but Momo, take a look at the syllabus, okay? Office hours only for questions that will not benefit other students. Okay, if you come to the office hour and ask me a question about a quest or some question, even a conceptual question, right? Even a conceptual question that maybe another student also has the same problem, right? Then you will get the answer plus some negative points, right? Because the negative points are necessary because you got an advantage and the other people didn't get an advantage, and some of them are doing it for a grade. Not everybody's doing it fun, right? So I got to even out the playing field. So if you want to come to my office hour, make sure your question is, confidential or personal and things like that. You can always check with me. Send me an email saying, I want to talk about this. Can we have an office hour, right? I might say, no, it's better to do this in the forum, okay? I posted a similar notion on the sub, not... Oh, there you go. Okay, so yeah, Andrew and Giorgio and a whole bunch of people, right? A whole bunch of people. Zeke. A lot of people have been playing around with data representation, converting their names and posting. So it's not just me. So if you have an office hour, you can only ask me, okay? So if you ask in the forums, there are so many people who can help you. Okay. All right, so we got 30 minutes. So, right, so we got, now we can have these switches in a row, and I can also control the position, the values of these individual switches. Now the question becomes, all right, now all I need now is a way to basically a convention, a contract between all humans or all, computer or, modern today's computer savvy humans, that this is the way in which we're going to represent information. So that needs to be in place. Number two is we need to have some way in which we can manipulate that information, right? Because, I could have all that information, but I need some logic and some mechanism which would say, now turn on that switch and turn off that switch, and turn on that switch and turn off that switch, right? So how does that happen? How do I send the current here? So I need to have some way of doing that. I don't think we'll have time to cover that. I'm happy to cover and talk about all of that ad nauseum at a different time, but it's not part of 2A, right? So we won't do that. We won't do that part. How that's computer architecture, by the way. If you want to know about those things, just enroll in computer architecture. I'm not teaching that, but I'll, but it's a good course, and there you'll get to know how these switches can also be, you can send an electrical signal and then it'll change, right? So then by, then you just need to choreograph the sending of those electrical signals, right? So, all right. So now that we have that, what are the kinds of information we want to represent, right? So can we start talking about that now? I think we're good on time. So yeah, yes or no? You want to talk about the kinds?
That's a good idea. Yeah.
So we want to represent free-form information like pictures, and we've already seen how to do that, right? Just pictures, we can just say dots, right? Dots. Pictures done. Okay. Anytime you want to say no or you can't do that, just let me know. Okay. Now, what are the other kinds of information? Pictures. If you want to do everything with pictures, it gets really expensive, right? So if I want to store the letter F, right? Letter F, which I see on my screen is forest, right? But store that as a picture, it's going to take a lot of bytes, right? Because if I look at that and I say, oh, there's a lot of pink dots and there's a whole lot of pink dots and there's a bunch of white dots here and so on. So it's going to take a lot of bytes just to store that letter F as a picture. Inefficient, right? So what I want to do is come up with a more efficient way of storing pictures, and so we did that very early in the stages in the history of computer science. We came up with a way called ASCII, right? It's called American Standard Code for Information Interchange, ASCII, and now it's called ASCII, right? ASCII is a code that we all agreed upon. That said, we'll use this code to represent a whole bunch of letters, right? So go to Wikipedia, for example. No, you don't go to Wikipedia. Think about Wikipedia, right? What are the kinds of symbols you see in Wikipedia? You see all the English letters, okay? And then you see the English letters in both cases, right? Uppercase, lowercase. So how many of them do we have? Uppercase and lowercase English letters.
52.
52. All right, thank you. Is that enough? Do I need anything else to store Wikipedia? Numbers, okay. How many digits? 10 digits, right? Yeah. Okay, so the 62. I need 62 possible symbols, right? Is that enough?
I think you have symbols too.
Yeah, I think we need some punctuation, okay? Punctuation. So yeah, symbols. And so throw in, I don't know, maybe 20 of those, right? 20. Let's say 20. Right, so 62. Actually, let's say 38. Okay, just to make it all a round number. So I need 38, which includes the digits and punctuations and those things. Okay. All right. So let's see. So punctuation. So we're looking at 100 symbols. Okay, 100 symbols. Okay. Now, is that enough? Is that enough? I think that's probably enough, right? With 100 symbols, I can represent anything in English. With punctuations and numbers. So which means pretty much the whole of Wikipedia. I can represent using symbols, using 100 possible symbols. Now the question becomes, how many switches do I need to have 100 different shapes, right? So the 100 shapes you can imagine a grid, right? A square grid, 10 by 10, 10 by 10, right? No, forget that I said that, right? So you have 100 possible symbols. How many ways in which we can arrange those 100 symbols so that each arrangement corresponds to a unique symbol, right? So I have 100 symbols and I have 100 switches. So I want to come up with 100 different shapes of these arrangements of these switches, right? Maybe all of them are on is one arrangement. All of them off, another arrangement, right? All the odd switches are on. That's another arrangement. So how many possible arrangements can I get out of let's say one switch? Two, right? Because that switch can either be on or off. Two arrangements out of one switch. Suppose I had like two switches, right? Two switches. How many possible arrangements? Four, right? Because I can have the first can be on, the second off, right? On, off, right? On, off, off, or off, on. So four possible configurations for two switches, right? So for three, how many do I need? For three, so this is eight, right? Eight. So yeah, so you can think about this, and it's very, and you find it's obvious that the number of possible arrangements you can get using n switches, right? So some x switches or a switches, some variable number of switches is basically 2 to the n, right? So 2 to the n possible arrangements can be got out of n switches. Okay, now how many arrangements do we need? We need 100 arrangements for 100 symbols. Yes? Okay, now how many switches do I need for 100 arrangements? Now we're going back the other way. Yes? So we're not saying how many arrangements can I get from this. So we want to go, how many switches do I need for that many arrangements? Okay, so we need 7 switches, because with 7 switches, 2 to the 7 is 128. So you're already getting more than 100 arrangements just using 7 switches. But we think back and say, hey, Intel and AMD, we're buying these packs of bytes in 8-bit chunks, right? But I only need 7. I got an extra bit. Okay, so what we can do is really say, I'm going to use more symbols than just what we have. So I'm going to have English letters, uppercase, lowercase, numerals, punctuations, and all these other symbols. I'm going to throw in some more funny characters, right? I'm going to throw in these box drawing characters like that edge, vertical line, and then a little circle, a degree, right? All these things, all kinds of funky characters. And you say, now with 8 bits, how many possible arrangements can I get? 256. 2 to the 8 is 256. Yes, so I get 256 possible arrangements. Okay, and 100 of those are sufficient, but then I'm going to use the remaining 156 to store all these fancy characters that I can use. So if you go to Google, right, go to Google or somewhere and look at, I think, unfortunately today, actually, I think I can share the screen here. Hang on. Can you guys see my other screen? Can you see my other screen?
To see the other screen, it would need to be the speaker, if anyone is using the speaker view. Otherwise, they'll have to tab over to your actual screen.
Oh, okay. All right. So you may need to switch over to my other screen, and let's say Google, let's say ASCII code. Okay.
Right now, we can see what you're typing on your browser.
Oh, great. Okay. So I'm going to type ASCII code. All right. Move this chat window out of the way so it's not concealing it. Oops. My tab is not working. Just move this out. Okay, now click on HTML ASCII reference W3 schools. Click on one of those. Click on that. Click on this. Where's that? Where's the image? Oh, it's still small. Let me make it bigger. Did it actually zoom up, zoom in your browser too? When I zoomed it here?
Yeah, it's enlarged.
Okay, it's large. Okay, great. Hey, that's funny. So they're only giving us 128 upwards. Anyways, you can see, right? You can see for every one of those, you have a symbol. So you see these really funny characters. Each one of those has a symbol too, right? And you can actually say, so that's what it is. You can transmit any one of these characters. If you sent me ASCII value 143, right? 143, you can code it in 1 byte, right? In 1 byte, 140. I'll show you how to code it in 1 byte. It's just a number, 143. And I know you were sending me that angstrom. Is that angstrom, or isn't it probably a Nordic letter, A with a little circle, a hat, right? So I'll know that's what you sent me. And you didn't send me that picture, but you just sent me a code, which is just 8 switches, right? You send me 8 values, ones and zeros, but as soon as I saw that, I knew that you sent me A with a hat. right? So we have these 256 possible symbols, and that's how we do it. Now the question becomes, right, so now we know how to store these letters and numbers, but I want to be able to store the number numerically, quantitatively, not the shape of the number. So if I look at the ASCII value, let's go back here, ASCII value of the letter A. I should probably use a different, oops, hang on, okay. I should probably use a different table. This one is crappy, okay? ASCII codes. We want to see early ASCII codes. Actually, the easiest thing to just do is do a terminal. Oh, but I'm not sharing my terminal. Okay. All right, maybe this one has it. Yeah, this one has it. Okay. And it's a better picture too. New tab. Oh, but I need to stop sharing this and share the other one, I think. Okay. I don't know. You guys can find out yourself. Okay, you have to click this, and then you can see this picture. And all right, there you go. Okay, so the letter A, uppercase A, is 65. It's only 65, and you know the number 0, I bet, is 48. Okay, it's 48 in decimal is number A. So if I send you the value 48, then you know that I sent you the digit 0, right? But how do I send you the value 48? Right? Do I send it to you as the digit 4 and then the digit 8? Then I end up with a chicken egg problem, right? This is a circular problem. Then I have to figure out how to send, you know, the 4 and the 8. So how do I send you? So I want to be able to send you the number, the quantity 0, the quantity 1. So that means I need to be able to represent the number using switches in a, what's a good word for it? In an arithmetic way. Right? Not in a symbolic way. This is a symbolic way. No, arithmetic meaning that I can actually do computations using, I can calculate it. So to do that, incredibly, we just use binary arithmetic. Right? Binary base is base 2. And if you've read module 0, this is basically what it's all about. Right? Base 2 is basically this planet where you only have 2 fingers, right? So you have 0 and 1. So you count in base 2. So 0, 1, and for 2, you don't have the symbol 2. So what do? You do the same, like I said, you know, in binary, anytime you're stuck in binary, you don't know what to do. Think back to what you would do in decimal. So in decimal, what would I do? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have a symbol for 10. So what do? I say 1, 0. That's a brilliant, right? Remarkable place value notation, which is so second nature to us. We don't even think about it. But it's a stroke of genius, right? To say that we can actually do it this way, so using place value. Right? So that's what happens, right? With all technology and science and innovation for several years, maybe even decades, right? People will marvel at things and say, well, this is fantastic. This is ground changing, foundational. It's going to change the way humanity develops, right? And after a while, it becomes second nature and we don't even remember it. Just like the frustrations that we were talking about last class, right? So when you're learning stuff, you know, there's all these frustrations that you come across, you face. But when you become an expert, you forget the frustrations, right? But you don't forget the frustrations, you can be a teacher, okay? Because then you can feel the frustration that the students also feel. And then you can resolve that frustration for the student, and then you can feel the same amount of relief that you felt or the student felt, or, you know, similar, right? That when they resolve the functions that you did, right? So that's the way I think it works. But anyway, so I want, and so you think back when you don't know how to do something in binary, you think back to decimal and say, how would I do it in decimal? So 0, 1, 2, 3, 4, 5, 9, then I say 1, 0. So in binary, you'd say 0 and 1. What is the next symbol? It needs to be 1, 0. So my 2 in binary is actually 1, 0, right? My 3 is 1, 1. And the 4 has got to be 1, 0, 0, right? So that's how you come in binary. It's exactly the same. Now, it's just another base, right? We think that numbers are so common and we use it all the time, but no. I need to stop sharing my screen for you to see the other thing. I don't know. Yeah. Okay. So what we want to do is basically say, all right, so I want to take that number 48. You can convert from one base to another, right? So if I say something, we just did, right? I said 4 in decimal is 1, 0, 0 in binary. right? 3 in decimal is 1, 1 in binary, right? So you can convert back and forth because it's a one-to-one map. This is exactly one-to-one map. So you can do these conversions. Now the trick is, can we figure out how to do these conversions for arbitrary numbers, right? Because instead of counting up, so if I ask you what is the binary value of 8, right? So you can always do it by counting, right? You can say 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, gee, where am I going with that? Okay, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 2, 3, okay? And then 4 is 1, 0, 0, 1, 0, 1, and so on and so forth. And eventually I can come to 8, which is 1, 0, 0, 0, right? That's, is a newbie way of doing this, right? The better way is to just do the conversion using the same way. How do you do this? Do the conversion. Think back to decimal, right? And I described this in the module, so I'm not going to go in module 0. So I'm not going to do this again in class, but I'm happy to do it, on in a separate session if you guys arrange it, or in Reddit, or one of you can do it. But essentially, in decimal, if I give you a number like 512, right? 512. How do you know it's 512? You take the number, and then you look at each of the digits, and you say 512. The rightmost digit is the weakest digit, right? It's the least significant digit. Is it because it's only 2? There are 2 units. But the digit next to it is bigger. In fact, it's 10 times bigger in magnitude, right? So its magnitude it increases by 10 each time. So there's 2 ones and then 1 10, right? 5 1 2. So 1 10, and how many hundreds? 5 hundreds. So 500 and 10 2. This is 512. Right? That's how you get it, right? That's the quantity. So the 512 is written like that, and looks like that. But in your head, 512 is a quantity. It's not written like that. If I open up your brain, I can't see 512. The quantity is stored, the quantity is stored in a completely different way inside of your brain. So that's a quantity. It's not the representation of the quantity, that's the actual, right? So that's also a representation of the quantity. But, it's a different representation. But how do you go from this representation to that representation? So how do you go from base 10 to base 2? And that conversion process is described in the module, right? It's very simple and straightforward, and I can do a session later on, okay? So you guys coordinate that and let me know, and I'm happy to come online and do the session, but I'm not going to do it now. But I want you to practice. Read the module 0 and practice doing a couple of conversions, right? In fact, not only from decimal to binary, which is the simplest of all, but actually that's not the simplest of all, right? Decimal to, binary to hexadecimal, maybe. It's even simpler. And hexadecimal to binary is also quite simple, right? So you do these conversions. In fact, you do the conversion base 27, that's a fun exercise, right? In fact, in data conversion quiz, you got to do base 27 conversion anyway. Yeah. So you gotta do these conversions, and then it will make total sense. And it's important. It's important to know, right? Even if you're not totally facile with converting back and forth, it's important to know how these conversions happen, and that they're all the same under the hood. They're all the same. You have to remember they're all the same under the hood. Okay, so I think we're approaching the end of class, and some of you have to leave in like 2 minutes. Well, actually, I'm gonna say don't leave yet, right? This whole thing with 9:50 and this 10-minute break between classes is all in part of the old world. Okay, because on campus, some after my class, I can understand it. But someone says, hey, I need to go to Andy's class, or Joey's class halfway across campus is going to take me 10 minutes to walk there. Or even if you have one of those scooters things, okay, I can understand. Right now, all you need to do is, let your fingers do the walking, like they say in Yellow Pages, right? So you don't have to walk. You just need to close this tab and open up another tab. You don't need 10 minutes. So our classes will run to 9:55 because you only need 5 minutes to take a pee. Yes? Yeah, I hope. Right. Okay. So I only need 5 minutes to water my plants because I'm going to take the 5 minutes to attend to my garden. So stick around for another 5 minutes. So yeah, what we'll do is during the early part of next class, maybe the first 30 minutes or so, we'll do some conversions. Okay, we're going to do some conversions. Actually, no, we won't do conversions. Do get comfortable with conversions before Tuesday. All right. And if you're not comfortable with conversions, ask me or a tutor or your classmates, someone, right, to set up a Zoom session, walk through some conversions. Hopefully by the end of today, I'll have an iPad so we can have so I can write and show you, right? And you can see like a whiteboard. We'll make sure the concept is firmly nailed into your head. So when we get to next class, what I'd like to do is talk about binary arithmetic, okay, how you can add and subtract numbers in binary, and how you can store negative numbers and floating point numbers. All of that will probably take about half hour. Okay, so on Tuesday, assuming that you're all completely comfortable with the representational issues, or at least you're confident enough to know that everything can be represented in one unique format, there's no confusion, right? Everything has to be a one-to-one map. So if you understand that they're all the same under the covers, okay, then we'll take it from there and do representations. And then after that, the second part of next class, we'll actually start coding, okay? And don't worry too much about the first couple of quests if you haven't done it yet, because I'll show you, right? I'll walk you through the first couple of quests on the screen, right? Not the quest itself, but I'll show you how to create the program for the very first quest. I'll show you how to fire up a compiler. We'll go with an online compiler for the first couple of classes, okay? For, cpp.sh or Replete, maybe something like that, right? Well, I'll get it up and I'll show you, this is how you open a project, you create a file, this is how you compile it, this is what you click to run it, and you see the result of your program. We'll go through that entire cycle, and you'll be surprised that entire performance will take no more than 5 minutes. Well, even with me talking, right? Me talking, that getting from start to finish, getting your first program done, no more than 5 minutes, okay? And then when you get your first program done, that's, set. You can, all you need to do is just take your first program and edit it, okay? One of the biggest mistakes that I find a lot of bigger programmers, more experienced programmers face is not like totally experienced programmers, but sometimes when you hire programmers, sometimes early in your career you'll have to hire a lot of newbies, right? So fresh graduates and so on, or people that know how to program but really haven't programmed on massive projects, right? So and then they get overwhelmed and start panicking, and they don't know where to start. Okay, and it is exactly the same. Again, like say, everything in life is basically exactly the same, right? When you're stuck in programming, is this the best way to deal with it, right? There was actually a movie, Sean Connery, and then there's this kid, this brilliant kid who could write English nicely. Forrest, something to do with Forrest, okay? Sean Connery, Forrest Whitaker. No, that's the name of an actor. Finding Forrest, Finding Forrest. I think it's called Finding Forrest. I saw it a long time ago, right? And why did I even talk about that? Anyway, we'll get to that. Okay, so but just go ahead and try to. And next class we'll talk about writing this code. Yeah. Okay. So when you don't know how to get started, and he's the same strategy that Sean Connery used to get that little boy. He's a brilliant writer, right? But he just couldn't get started on an essay, right? And some of you are enrolled in English courses. You got to write essays, or you just have product design courses, and you got to design a product, or whatever it is, right? So most people get stuck, right? And it's called a writer's block, or a designer's block, or a programmer's block, because you don't know how to get started. The best way to get started is always to get something that's already been done by someone else or by you, right? And this is a Hello World program that you're going to write next class is going to be it. Start from that and start chipping away and adding more, okay? When you have something to work on, you'll find that incremental advances are easy. But when you have a blank slate, it's really, really hard, okay? So like an essay, right? Write some total crap. Get total crap down, right? So maybe if you have to write an essay in English, just write anything that comes to your mind, right? Don't worry about grammar or syntax. Just write down anything you want. You don't have to show it to anyone, right? So only you are going to look at it. Then after you've got all your thoughts down, 99% of those will be rubbish and junk, right? I presume, right? So cut it all out. Even after cutting it all out, you'll find that 3 or 4 sentences survive. Okay, that's the basis for your new thing, and those are like the good seeds, right? You buy a pack of seeds on Amazon, you get 100 seeds, 100 seeds of morning glory or something like that. Maybe not all of them will germinate, right? So you got the pack, you got to throw it out, and then in a few days you go and see which ones germinated. Like that, like that, you could do this, right? So write down everything, or take an existing program which doesn't even do what you want it to do, and then say, well, this is what I want to get done. And like I said, you have to be 100% clear in your own mind as to what you want to get done, right? Just like in life, you need to know where you're going. If you don't know where you're going, you're not going anywhere, okay? So you know what you need to get done and you know what you have. You have the starting point and the ending point, right? If you don't have one of those, you're basically screwed at that point, right? You have to have the starting point. Doesn't matter where the starting point is. You want to go to San Francisco, but right now I'm basically in Timbuktu, right? Someplace in the middle of Africa or somewhere, right? So, but you know the starting point and the ending point. You can plot a course. But if you don't know either of these, there's no way you can go, right? So I'm in Timbuktu, but I don't know where I want to go. I'm not going anywhere, right? I'm in Timbuktu. I want to go to San Francisco, but I don't know where I am. You're not going anywhere. So first most important rule of programming, of writing, of designing a product, know where you are, know where you want to go, okay? Don't care, don't be worried, okay? All people always worry about what's in between, but how can you worry about something that you can't see, right? You got to see something and then you can manage your way around it. So the middle you can't see, you can only see the ends, okay? So get the ends fixed in your mind and then you can weave your way to the end, right? And so get your old program that we'll write next class, okay? That's going to be a basis. And then your next program, you take the old one and modify it, okay? And then by the time you get to your 15th or 20th program and you want to do something, you'll find that you don't have to go all the way to the first program. You'll actually find one of the programs that you wrote in the past, right? Maybe in 10 years ago or 5 years ago or 3 years ago, right? Maybe that fits the bill, not perfectly, but it does a lot of things that I need to do. So you can take that and make just a few changes here and there and you got, right? So that's how it happens. The more programs you write, the easier it'll be for you downstream later on in your life, because you can just basically pick and choose and put these together. So what you're going to do is basically starting out with these mini Lego pieces that you're going to get starting from next class, not physical real Lego pieces, these programming chunks, basically these little ideas, the mini Lego pieces. You're going to get these, you're going to get a lot of these, okay? And in your career as a programmer or computer scientist, you're basically going to say, I'm going to put 10 of these pieces together and get a tree. Okay, 10 of these pieces together, I'm going to get a building. But these, I'm going to use lots of buildings. I'm going to use lots of trees. So what I'm going to do is make lots and lots of trees, lots and lots of buildings. This is easy to make. In fact, I'll just teach my dog how to make these trees because, you don't have to be a human to make these trees. Okay, and my dog has a lot of free time because all the time he's just sitting there wagging his tail. So I'll get my dog to make a lot of trees. So, and I got like a billion trees now. And you use these trees. So likewise, your programs, you'll get more and more sophisticated programs, lots and lots of sophisticated programs, you copy and paste, right? Like your dog. And then you can build bigger and bigger artifacts using things that you have built, right? That is the beauty of any field, really, not just computer science. So was this class better than last class, more useful, or is this format working for you guys? Are we covering enough material? So just give me some quick feedback so while you take off. Before you take off. And great, thank you, Daniela.
Yes, it was great.
Excellent. And and it works out for me because I'm sitting in a very comfortable position. Cross-legged is the most comfortable for me. Although you can't see it, but yeah. And so I can lecture like this for 10 hours if you want, right? So 10 hours, it's perfectly fine. Well, you take a break for 5 minutes from here and there, and keep in mind that anytime you want me to give you a special class, I look forward to these classes, okay? Because you will too, right? Once you know some stuff, you will get a great deal of enjoyment out of sharing that with other people. Yeah, there's a great deal of enjoyment in sharing itself. Yes. Okay. So and you'll find that, and I love it. So please, if you want me to have another classes, absolutely, right? So get together. But I'm not going to do a special class for just one person or two people, right? So then, well, maybe, I don't know, maybe we record it but we'll see. We'll work out but the more people, then the better it is, because then people will ask questions and then you can bounce off each other, and it actually works out fantastically, okay? And with time, we'll have more, free time here and there. And sometime I'll say, well, for the next 20 minutes, you guys are going to be coding this, and I'll just, take off, maybe take care of my plants or something like that, do some chores around the home while you guys are working, and you can call out for my help, okay? So we'll do it that way. Thank you so much for attending class today. Are you guys coming back next Tuesday?
Yeah, of course.
Okay,
Yep.
thank you very much. Yeah, we'll see you next Tuesday or earlier if you guys want. Okay. All right. Thank you so much. And let's end the meeting. I'm going to try. This is recorded, so I'm going to put it up on YouTube like last time, and we'll see how it goes. All right. Thank you. Bye.
Okay. Thank you.
Thank you,
Yes,
Professor.
I can see it. I can see it.
Thank you.
All I can see you. Yes. Yes.
Thank
In
you.
case anyone didn't see it on the chat, Momo and I are going to do a quick study session on Zoom after this class about data representation. Everyone's welcome to join us, and if you want the link, it's in the chat window, and I can post it again if anyone
Can you
wants
post it also on Reddit, because some people will have Reddit notifications.
I can put it on Slack.
But yeah, I don't know if everybody knows about Slack yet. And this is the point I made about Slack is that, you know, some of the more experienced people, it's a no-brainer. But
Sure.
yeah,
I can post a quick post on Reddit so people can have the link.
yeah, because the beginners will get totally confused. I mean, many people don't even know about Reddit or Slack or even Canvas, right? And they don't know where to go. And they don't know anything about Slack. So let's let them discover Slack. Maybe in 2C, right? When you get to 2C, Slack might be a fantastic place to collaborate. But yeah, to take a note of, you know, Saul is holding this. Hey, Saul, also check in with the STEM Center and Lane and to see if they're doing any tutorials. And then that might be another resource that you guys, not now, because now it's all very simple. But you can, yeah, you can do the data representation quiz as long as it's open. And in fact, even the first quiz, the prep quiz is open, right? So you can take it when you want. And obviously, those of you who are on the waiting list need an ad code. You still have time until Friday, I think, yeah, to complete the first 5 quests. But those of you who already made it into the course, you don't have to do this. But those who want an ad code at this time, at this point in time, they have to complete the first 5 quests to get the ad code. And I think it's reasonable because, you know, my time is committed to you guys, and additional people that come into this class, they're going to be taking your time away, essentially, right? Indirectly. And so it makes sense for me that they come in prepared so that not only are they able to, you know, participate in class, they can help you guys also, right? Make up for, you know, compensate for taking away your time by giving their expertise. So they have to complete the first 5 quests. You have time. If you're on the waiting list, you have time until Friday, right? Anybody else who wants to enroll in this course, fine, I don't care. It's all Zoom and I'm talking here. So feel free to tell your friends to come in and, you know, they can do the quest for free. They don't have to enroll, but yeah, they can enroll. I'll give you an ad code if you complete the first 5 quests by Friday. Anybody, okay? I can have 1,000 students, you know, do the quest and do all of you in class in Zoom. No problem, because I'm not Zooming 1,000 streams. I'm not sending that much bandwidth, you know, that much data out of my pipe, right? Google or Zoom is going to, you know, send the data out. So it's not even data cost for me. All right. Thank you guys. Bye.